Yeah, now it's recording.
Excellent. Okay, so thanks for everyone for coming and for tuning in. So today we're very happy to have Brian Swingle from some superposition of Maryland and IAS, who's going to tell us about various aspects of holographic complexity. So Brian, thank you very much, and take it away.
Yeah, great. Thanks for the invitation and for coming out to listen. Yeah, I'm going to tell you basically two stories that are from two recent papers. One with my student at Maryland, Yixu Wang, and the other with Cesar Agon, who's now at Stony Brook, and Matt Headrick at Brandeis. And I'll tell you more about what these stories will be about in a little bit. The first thing I'm going to do is review very quickly the background of this holographic complexity story, what it's all about, why we're thinking about it. And then I'll tell you about the two works and what they sort of tell us about how to make sense of this correspondence. Okay. And everything here is supported by it from Qubit. So that's who you have to thank for this. So let's remember the basic setup of the holographic complexity story. The sort of starting question was, you have, say, a two-sided black hole in anti-de Sitter space, which, according to Molosena, is dual to a pair of entangled CFTs in what's called a thermofield double state. So this is a state that's essentially a purification of the thermal density matrix of one side alone. So the black hole entropy is interpreted as the entanglement between the left and the right. And what's interesting about this geometry is that if you look at observables from the point of view of either side, or even two-sided observables, they quickly sort of thermalize after a relatively short time. However, if you look at the interior, the future interior of the black hole, which is this, let's see, I think I have a pointer.
Yeah, we can see your mouse, or normally we can.
Oh, you can see my mouse, okay.
Yeah, just don't move it
so
too.
This region up here, which is the future interior of the black hole, it has the property that it changes with time, even at very late time. In a certain sense, it gets longer. And the question was, what does this mean? So a little bit more precisely, there we go. If I say, look at the volume of a spatial slice anchored at two different times on the boundary, then at 0 time I have this nice slice I have time reflection symmetry. And then as I increase the time on the left and the right, then the maximum volume slice looks sort of like this as I go up, and you can find that its volume increases roughly linearly with the time on the left and the right. So the initial wormhole is over here at sort of some relatively short thing where there's the horizon bifurcation surface here in blue. And then as you evolve in time, this wormhole gets longer and longer and longer, well after, say, the entropy has saturated or other simple observables have come to equilibrium. So the natural question is, what does this mean in the CFT? And the idea is, originally, I guess, due to Susskind, essentially, and also building off of work of Hartman and Molosena, is that this is somehow related to the complexity of the quantum state, or from the point of view of Hartman and Molosena, something like the minimal tensor network you would need to construct this quantum state. So here I show the thermofield double, just to remind you, I have this pair of entangled energies on the left and the right, with the square root of the Boltzmann distribution here. And then time evolution, where I move up on both sides, corresponds to adding this phase factor, which depends on the total energy. And the rough expectation from the point of view of the CFT is that the change in complexity of the state should be roughly like the number of degrees of freedom that are active, the sort of computing degrees of freedom, which is the entropy S, times their computational rate, or their rate of scattering, which is roughly the temperature T. So in other words, each of the S degrees of freedom scatters or complexifies or applies some elementary unitary dynamics roughly every 1 / temperature time steps. And so you would expect the total complexity to increase roughly like temperature times the entropy. Just to be clear about what we have in mind here, if you think about this, the CFT ground state again for a second, then you have this empty anti-de Sitter space. And the idea of the tensor network point of view is that we should basically fill this space with some kind of say, Mera-like network, some network which captures the renormalization group structure of the quantum state, the fact that it's a scale invariant state. And then if we turn on temperature now, then we have, again, the wormhole picture. And the idea is basically we glue this renormalization group part on the left, which is this kind of orangey triangle trapezoid thing here, to another renormalization group part on the right, which is this other trapezoidy thing. And then in the middle, they're connected via this wormhole, which is essentially evolution, this kind of linear evolution network, where the number of legs here is the entropy. So essentially, I take my RG network, I renormalize down to the thermal scale. That's the horizon here. Then those degrees of freedom evolve. Their natural energy scale is the temperature. So the natural rate of computation, if you will, is the temperature. So those S degrees of freedom evolve at a temperature scale for however long I choose to evolve them for. And then on the other side, I, again, sort of convert those entropy degrees of freedom back. I embed them again into the UV Hilbert space. And that's what the RG part does. So the very rough idea of these early works was that the complexity is basically just the number of little blue blobs in this network, the number of tensors. And each tensor should count, say, as like roughly a central charge's worth of complexity. The first way to really measure this in a nice way is called complexity volume duality. This is due to Susskind and Stanford-Susskind. And the idea was that basically I should compute the spatial volume of this maximal volume slice I showed you before. That's unitful. The complexity itself is a unit less. It should just be like a number of operations or number of tensors. So I divide by some factors. They suggested that I should use Newton's constant and the ADS radius. And if you do that, you indeed get this TS that you expected on CFT grounds coming out. Essentially because the volume of the wormhole is roughly the time times the temperature times the cross-sectional area of the horizon times the factor of the ADS radius. And so it all comes out in the way you like. Here I want to emphasize that the complexity is supposed to be viewed in this way of thinking as the minimum number of operations you need to produce the state. So you need to sort of look over all possible tensor networks or all possible circuits and find the one that has the minimum number of ingredients. But there's lots of not assumptions, but lots of pieces that go into this definition. For example, you need to choose where to start. That's called the reference state. You need to choose how you can move around, like what gates you allow. That's the universal gate set. And in general, you may not be able to exactly replicate the state of interest, but only approximately. So there could be some tolerance parameter. So there's quite a lot of ambiguity in this definition. I mean, there are a lot of choices you have to make. And so you might, sort of wonder, one immediate question from this kind of proposal is, what exactly does the left-hand side mean? What is this complexity supposed to be? And I think that's still a question that's open to some extent. We have made a lot of progress in other contexts, but I think it's still, precisely how to interpret the complexity is not completely clear. I'll come back to that later on. One useful idea was to sort of adopt a continuous time notion due to something, a sort of geometric notion of complexity due to Nielsen. And, we could speculate that maybe there's some continuum way of dealing with this, which plays nice without having all this qubit structure. And I'll mention more about that a little bit later. Then came complexity equals action, which was a sort of, depending on your point of view, an enhanced proposal or sort of just an orthogonal proposal. But they said, well, they, including myself, said, why is this sort of single spatial slice special? Maybe we should really look at this whole space-time region, the Wheeler-DeWitt patch, shown in gray here, which is sort of all the region in the bulk that should be related to the state of the boundary at these times t left and t right equals little t. And because we had to choose this arbitrary length scale in the volume proposal, maybe we should somehow get rid of that by looking at something more dimensionless. And the natural quantity to think about is the action. And so we propose that you should essentially look at the action of this Wheeler-DeWitt patch, compute it with some rules, and that action would be the complexity. And sort of remarkably, it turns out that this also works and gives you a growth rate for action, which is proportional to temperature times entropy. In fact, it's exactly equal to twice the mass for a black hole in any dimension. And so it was sort of, again, seemed to nicely match the expectation on the CFT side, but had seemingly less arbitrariness in it. There was no length scale to choose. And so in particular, you could push it to regions, to sort of new limits where you couldn't apply the old proposal, or it wasn't clear. For example, with a charged black hole, it wasn't clear what length scale you should put in there. If you just use the ADS radius, it wouldn't work in general, meaning it wouldn't give you temperature times entropy. Whereas the action proposals seem to work over a broader range of parameters. Okay. And I'll just mention that this again works roughly because now the space-time is essentially this sort of spatial geometry of the long tube times roughly an ADS radius in the sort of radial direction. And that's why essentially everything works in the simplest possible case, while they all give compatible answers. And there's evidence from shockwaves that this sort of network is actually, in some sense, minimal. That is, you're canceling parts of the network you don't need. But I won't go into that. Okay, so that's kind of a very, very fast recollection of what the motivation was for this story and what the basic story was. Since that time, there's been lots of progress in many different directions. This is only a subsampling of all the possible directions that people have thought about. Some of that will be important for us are improvements or better understanding of the basic rules for calculating actions. The problem is that these actions involved regions where you had null boundaries, and it's a bit confusing to make sense of the action of general relativity in situations where you have null boundaries. So in very nice group work from the perimeter group, they sort of worked hard and thought about this carefully and came up with a set of nice rules that tell you how to calculate these actions in a consistent way. A nice output of those rules is that you got the same result that we found in our original calculation, but you understood a little bit better the various choices you had to make in getting that. And there's also just been an enormous number of people computing these actions and volumes for different kinds of theories. And there's also been applications to new sort of physical questions. So previously we were thinking about complexity of the whole state, but we could also think about the complexity of, say, subsystems. Can I make sense of what it means to say, can I make sense of the complexity of a subset of the CFT degrees of freedom, which are, say, in a mixed state of some type? Does that make sense? So there was pioneering work here. And we'll talk more about this a little later. Now, another interesting direction, sort of the other side, the C equals A has two sides. So this first part is really about the A part, or the V part. And the other side is the C part, the complexity, which is really a field theory notion at its core. And I think one really nice development there has been, at least for simple free field theories, much improved understanding of what the complexity could actually be on the field theory side. That is, one can really take this Nielsen approach seriously, write down a set of gates, meaning unitary transformations, and write down a sort of a complexity geometry and actually calculate the lengths of curves in that geometry and find the minimal curves, and then really show that you're getting something that looks roughly like what you get in ADS-CFT. So of course, ADS-CFT is not a free field theory, but these complexity ideas are sort of sufficiently robust that it may not be that sensitive to the precise interaction structure. Now, some things matter, some things don't, but there's a lot of beautiful work here, and I think this will probably be the starting point of the way we really understand ultimately in field theory what the left-hand side, what the complexity really means. Another interesting development is in the complexity action paper, we conjecture that maybe black holes are the fastest computers, or the fastest complexifiers for some given energy. It's actually been shown by Stephen Jordan that that's not true, in the sense that you can actually compute arbitrarily fast at a fixed average energy. So he really came up with just a sort of qubit computational model, which I can explain if you're interested, where he showed that basically you can apply quantum computation at a rate which can become arbitrarily large, even with fixed total average energy of the system. So that's kind of a nice construction. we had some artificial examples in our paper where you sort of superpose two different energy states of very different energies. So the average energy could be small, but the complexity could grow like the complexity of the higher energy state. So we sort of knew it wasn't really going to be an exact bound. Stephen really showed very clearly that there's no such bound at all. But it still seems possible, or seems like there's something to understand about what's special about these holographic models where you do sort of get this temperature times entropy or mass of the black hole fairly universally. Okay, so let me pause here now. I'm going to go on the next stage to talk about the recent works, but let me pause here and ask if there are any questions or anything you'd like me to clarify what I've said so far.
Oh, I think we're okay here in Potsdam, unless somebody has a question.
Great. So I now want to tell you first about a paper with Yixu Wang, who's my student at Maryland. This is the archive number. You can find a much more complete list of references there, as well as all the details of the calculation. And this is really a paper about trying to extend this complexity story to an interesting class of geometries, where you have a different kind of scaling symmetry. And what's sort of interesting about this class from the point of view of the complexity story is that the tensor network you would need to describe this geometry is quite different from merit. It has a more elaborate, a richer structure. So if we can actually match the tensor network to the holographic calculation, then we've really sort of gone a little bit beyond the story that was there before. We've matched the complexity to something holographic for a sort of much broader class of theories, where there really is a qualitative difference between this class and simple CFTs. So the theory, to be precise, that we consider is an Einstein-Maxwell-Dilaton theory. So there's your standard Ricci scalar term, the gradient of the scalar field, which is the dilaton. There's some arbitrary dilaton potential, and then the dilaton also couples to the field strength of the electromagnetic field, the Maxwell field. And we look for solutions to the equations of motion of this theory, which have a scaling form where I have some quantity L, which is roughly the ADS radius, something like the ADS radius, and then some arbitrary functions, f of r and g of r, in front of the TT and RR components of the metric. Right? And the gauge field also has some radial dependent profile. And we need to specify these functions v and z, the couplings and the dilaton potential, but with some relatively natural choices there, and which involves some parameters alpha and beta, seen here. Then you can find solutions to the equations of motion which have the structure of power laws. So here is the function f of r. There's lots of constants and whatnot. Don't worry about those details. The point is, you see here there's an r to a power. So f is a power, g is also a power. Here's r to a power. H is a power, and this e to the phi is in general also a power. So everything's a power law. So it's some kind of, it smells like a scale invariant solution of some type. What's interesting about the solution is that it has a generalized scaling symmetry, where I take lengths to some factor lambda times length. I take the radial coordinate to some factor which depends on a new number called little theta, which is the hyperscaling violation exponent. Little d is the dimension of the boundary CFT space, not space-time, but space. And then also the time scales differently than space in principle. I have a factor of lambda to a new number, little z, which is called the dynamical exponent. And then the metric also scales in some way. And if you make this scaling transformation, you can see the metric is invariant up to this factor. So it's some kind of generalized scaling symmetry where length and time scale differently. That's the dynamical exponent. And also, in some sense, the dimension of space is different from the naive one. This theta is like a deficit in the dimension of space. These kinds of solutions are interesting in part because there are condensed matter systems. For example, if you take fermions and place them at finite density, non-interacting fermions, for example, at finite density, then they form a Fermi liquid state, really a Fermi gas, where there's a finite Fermi surface in momentum space with all the fermionic states inside this surface filled. and all the states outside empty. And it turns out that that state of matter has this kind of scaling symmetry where z is equal to 1, so space and time still scale the same way, but this quantity theta is actually equal not to 0, which would be the case for a CFT, but to d minus 1. And that corresponds to the fact that the excitations in this theory are not located at a point in momentum space, but actually on a whole codimension 1 surface in momentum space. Okay, so this study of these solutions arose out of a desire to have some holographic models which mimicked metallic states in condensed matter systems. At least that's one motivation. Here we study them because they just have a qualitatively different scaling structure, and we can sort of try to probe that scaling structure with complexity and see if we can match it to some tensor network. The calculation is the usual one. Now we have lots of terms. We have the bulk action here. We have these bulk actions. We have, yeah, this is the precise notations here don't matter. There are corner terms and surface terms. These things all follow from the analysis I mentioned before by the perimeter group. And you can make the calculation at the long time limit. You find the action growth rate is proportional to twice the energy. That's twice the mass of the black hole, times an enhancement factor of 1 plus the dynamical exponent minus 1, divided by the dimension of space minus the hyperscaling violating exponent. So in other words, if the dynamical exponent is 1, then you just recover the CFT result. If it's different from 1, then you actually get, if it's bigger than 1, which we think is needed for causality, then you get an enhancement of the action growth rate. It's actually bigger than 2n. So this is actually one example of a holographic model which violates the conjecture that 2n was the maximum rate you could have.
So Brian, is this correction term sign definite?
Yeah, so the general expectation is that this z has to be bigger than 1 for a local theory.
Okay.
Now, people have also talked about, and I guess there are some examples where you can think of theta as negative, but I think theta doesn't usually make sense to think of as being bigger than d.
Okay.
So in the examples I know, this is always a positive number here, and so it goes faster. But there may be some other funny example where you can have a different behavior, but I'm not aware of it. In all the sort of reasonable condensed matter or field theory examples where you get this kind of physics, I'm not aware of any example where this would be negative. You can also compute volume. I won't go through the details, just to say that the final thing here is important, which is that you get the energy times a factor of the temperature to some funny power. And what this means is that you remember in the volume calculation you needed to pick a length scale. So here you'd have to choose actually a temperature-dependent length scale in order to get actually the expectation of the growth rate should be like the energy out again. So it seems sort of more, well, you need to make more choices, and the choice needs to depend on the temperature in some way, which may or may not be a little artificial from some point of view. Now, how can we understand this theory from a tensor network point of view? The idea is that we need a kind of branching structure to the tensor network. This branching structure occurs because we have this non-zero exponent theta, the hyperscaling violation exponent, which I said is associated with the fact that you have, instead of excitations at one point in momentum space, you have sort of excitations everywhere on some codimension 1 surface for the simplest Fermi gas situation. So the expectation is somehow that theta represents the fact that you have more low energy modes than you would naively expect. And in an RG, you can think of this in a precise way by imagining that every time you coarse grain the system a little bit, by a factor of 2, say, you also break off different copies of the system, which exist at that coarse grain level. So you start with, say, the Hamiltonian on a large number of degrees of freedom here at the stop. You do one RG step. If it was a conformal field theory, you just get one state down here, one coarse grain state. But for these hyperscaling violating theories, we believe that what you need is actually you need to get multiple copies of that coarse grain state. The number of copies being 2 to the power theta. So it's sort of like you have this, it's it's like you have a bunch of wires. I think you can imagine having a bunch of wires, parallel wires. And as you coarse grain those wires in sort of the direction of the wire, you also have to separate out the wires in the transverse direction, and you get sort of 2 copies of wires on the smaller size scale. And this kind of construction goes back to work by Evan Blaine Vidal called branching mirror, and then a work I did with John McGreevy called s-sourcery. The idea being that you need, again, more copies. You need just 1 copy of the smaller size system to make a bigger size system in Mera, like flowing up the RG. Here you need multiple copies to fuse together to make 1 bigger size copy. But the point here, the details are not super important. The point is just that this is a definite tensor network structure. And what we can argue is that this tensor network structure would actually recover that complexity growth rate that we had in the holographic model. Let's see how that works. So here, sorry, I was a little lazy, so I just copied part of the paper. Let's think about the following situation. You have some lattice constant little a, that's the UV scale. And you have another scale C, which is a length scale. That's the thermal scale, the sort of scale of thermal correlations. For a theory with this hyperscaling, with this dynamical exponent little z, the thermal scale would go like, oh, that's wrong. It should be t to the minus 1 over z, sorry. The thermal scale should get longer as the temperature gets lower. And so the idea is what we want to do is we want to coarse grain the system until we reach that thermal scale. That's what I said before was the interpretation of the horizon. It's like I renormalize until the cutoff is of order of the thermal scale, and then I can't renormalize anymore, and I have just my thermal degrees of freedom. So I'm going to perform little n RG steps, which is how long it takes me to renormalize from the lattice scale to the thermal scale. And the idea is, as I said, you take this Hamiltonian. So this is a little piece of the time evolution for infinitesimal time step delta t. You apply this isometry n times to it. That's the renormalization isometry. And what you get out is now the time evolution acting on the thermal scale degrees of freedom, where I have the identity still here. I have a factor here related to the fact that the Hamiltonian gets renormalized. That's like changing the energy scale. And then I have a bunch of different copies of the Hamiltonian here. That's the different copies. And you can see the number of copies is 2 to the n theta. Because I get 2 to the theta copies at every step, and each of those copies will make 2 to the theta more copies, so the total number of copies after n steps would be 2 to the n theta. That's what I've shown explicitly here. The density matrix of the Hamiltonian at the microscopic scale sort of turns into, roughly speaking, 2 to the n theta copies of the density matrix at the thermal scale. Now, how many sites would you have in such a system? Well, you've taken the original capital L sites, say, and you've renormalized that to the thermal scale, which is the C. So the number of sites, which is that ratio of links to the d power, goes like the total system size times the factor of the temperature to the t over z. The number of density matrices you have, the number of copies, which is 2 to the n theta, well, that's give you the thermal scale divided by the lattice scale to the power theta, using this formula here. And that, if I convert to temperature units, is like some kind of UV cutoff energy scale divided by the temperature, again, to some funny power of theta minus c. Now, if you put all these things together, you look at the number of sites. That's the number of degrees of freedom in each copy, the number of copies. And then each copy has a natural scale of the temperature. That's the energy scale. So it computes at a rate t. You put all these things there. You get the volume. You get a funny power of t to the d minus theta over z. You get another power of t for the computation rate, and you get a time t for how long you computed. That's just integrating up the infinitesimal dt here. Now, what happens in these hyperscaling theories is the entropy as a function of temperature is given by the volume times this power t to the d minus theta over z. So what you see here is actually you get exactly out the entropy times the temperature times time. And you really need this branching structure to get that, because you need to somehow effectively reduce the power of temperature that appears here. That's what the role of theta is. That reduction, the power here, is what's coming from having these multiple copies. And so I'm not claiming this is, an existence proof that this tensor network describes as holographic systems, but it seems at least to capture, roughly speaking, the right number of degrees of freedom and the right scaling with temperature. And I can tell you that for some simple models, we do know this tensor network will capture this kind of hyperscaling state, but in general, we don't know for sure. So this is sort of still an open question here, but at least we've made the first step of sort of mapping these two different calculations onto each other. Okay. So the conclusion of the study is that we can study this theory. It's straightforward to apply the usual rules. We get an interesting action growth rate out of it. The complexity calculation, the volume calculation doesn't sort of look as nice, although you could just choose a length scale to make it match what you expect. And moreover, there's a nice tensor network which seems to recover the expected complexity growth rate. So maybe we have some more non-trivial evidence now in a new class of theories that there really is a kind of natural mapping between these two quantities. Okay. So I'll pause here again and take any additional questions you have.
So Brian, is there some modification of this tensor network picture if you consider a charged black hole, or basically the same story goes through? I mean, I'm talking even about like the standard fluid gravity, classical field, and bounding scales.
So I don't think I quite called everything, but you were asking about charged black holes?
Yeah. So I was asking that over here, like you have like a very nice heuristic picture of behind the growth based on the tensor network language, right? So I'm asking, like, if you consider a charged black hole, is there some modification to this picture, or basically the same picture applies?
Yeah, great question. So actually these black holes are actually charged.
Oh.
Because basically part of this story was about if you take the theory without the dilaton, then you add the charge, just Einstein-Maxwell, you get the extremal black hole or the near extremal black hole, which is kind of weird from a condensed matter point of view because of the entropy density at zero temperature. So part of the motivation for these theories originally was to get rid of that feature, and the dilaton can do that by renormalizing the coupling. If you go back and ask about, so these actually do have charge, although you don't have, I mean, this is just the way it's realized in that theory. You can get these solutions in other ways. If you go back to the extremal black hole, then I think the picture is a bit different. And we don't have a very good tensor network picture of that near extremal black hole yet, because you have this long throat, and there were old puzzles about the complexity growth rate and the bound, the conjectured bound for these charged black holes, which we didn't resolve in our original paper. And I think there's still kind of something the field is wrestling with.
Thanks.
Yeah. All right. So in the remaining time, I will tell you about this other work, which is about holographic subsystem complexity. This is appeared earlier this year with Cesar and Matt. And the motivation here is somewhat related to the previous case, where we're trying, first of all, to understand the difference between complexity equals action and complexity equals volume. Whether they're sort of really both measuring complexity, or they're measuring different things. And interestingly, in this situation, we're going to find a fairly dramatic difference between the two of them, in principle. We also wanted to understand more about subsystem complexity, because that's a situation where we have, where again, there's sort of qualitative features that the tensor network predicts that one could try to match to some holographic calculation. So we have definite expectations for various properties of this complexity coming from the tensor network point of view. And so maybe in this new setting, we can match some of those, qualitatively distinct expectations to something in the holographic side. And as I mentioned earlier, we're not the first to think about this subject. There's a nice literature already. Our contribution was to study a special simplified case where we sort of look at just one side of a two-sided black hole. So that's very nice because there's no spatial structure to deal with, and the calculation is very simple. And the interpretation is sort of easier to make. And the other thing we did was to study in detail and make some proposal for how you should interpret on the complexity side, on the sort of quantum information side, what the left-hand side, what the complexity means precisely. there's actually a rich zoo of possibilities, which I'll discuss a little bit later. And there's an interesting question about which of these, which beast in this zoo is actually giving you the holographic answer, if any. So here's the proposal. Two-sided black hole again. W is the entanglement wedge of the two sides. And the idea is what I should do is I should take, if I'm interested, say, in the complexity of one side of this two-sided black hole, which is in a thermal mixed state, I should take the entanglement wedge of that one side, which is the whole outer part here in red. I should intersect it with the entanglement, with the Wheeler-DeWitt patch, which is the blue, and I get this purpley region in here, this square. I compute the action of that square, or the volume between the boundary and the RT surface. And that volume or that action is supposed to be the complexity of the subsystem corresponding to just the left. Okay, so the proposal is very natural and reasonable. Now let me tell you about the results that we get from this calculation. So the first feature that comes out quite generally is that for volume, the complexities are super additive, which means if you take, say, the whole thermal field double and break it into left and right, or more generally into any region A and its complement AC, then the complexity, the subsystem complexity of region A plus the subsystem complexity of region A complement is always less than or equal to the complexity of the total thing. The reason why is that the left and the right are both constrained to pass through the RT surface. So they're a constrained problem, constrained maximization problem. And so because the right-hand side is unconstrained, doesn't have to pass through the RT surface, it could in principle be bigger. So this is a completely general inequality that's obeyed by CV, by the volume, which is a trivial geometrical fact. But it implies that you have this inequality, the superadditivity of the complexity as measured this way. And in fact, at zero time, as evident from this picture, the complexity of the thermal field double is just the whole length across the time equals 0 slice. The complexity of either side from the volume point of view is just half of that. It's just there. So twice the subsystem complexity of the left is equal to the complexity of the total thing. So it actually saturates this inequality at time 0. Now the story with action is more complicated. In the paper that we put on the archive, we did the calculation without what's called a counterterm, which I'll explain briefly in a moment. And there we found that the complexities are subadditive. I mean, the complexity of the left plus the complexity of the right is actually bigger than the complexity of the whole thing. And that was nice because it's sort of different from volume, so that was a qualitative difference between the two of them. And moreover, the inequality is not saturated at time 0. It's strictly unequal.
So Brian, I have a question about the second inequality, so about subadditivity. So what do you know what happens if you include this counterterm? And second, do you have an idea if it holds more generally, or but this is something that is based just on this one example of the term of double state?
Yeah, great question. With the counterterm, which is this thing here, theta is the expansion on. So you have these null surfaces. You have some parameter lambda, which is a affine parameter, which like labels. You know, you think of the null surface as like a bundle of generators. Lambda labels the motion along the generator, and x is a transverse coordinate. Theta is the expansion of that null congruence, and you have this so-called counterterm. The role of this thing is to essentially cancel some ambiguities in the way you normalize the corner terms, among other things. So it makes the whole thing reparameterization invariant, and it's sort of a nice term that was buried in the appendix B of the perimeter paper, but sort of slowly seen the light of day and actually turns out to be fairly important, it seems. And with this term, you can do a calculation. It's relatively easy to evaluate this term, and you find out that the sign of this inequality actually depends on the choice of this quantity, little lc. So this quantity is arbitrary. It's not fixed by anything in the prescription. And depending on what lc is, you can either get that the action is subadditive or superadditive. So it seems that actually there's not a definite answer for CA. Or maybe, you know, it comes down, and I'll touch on this more at the end, it comes down to what you choose for this counterterm. And as far as I know right now, we don't have a very well-motivated choice.
And these statements are based on the thermal field double example. Not
That's right. This is the thermal field double. So this statement about volumes is quite general. I mean, it's just a geometrical fact. It's sort of trivial. But these statements are really, we only check them or study them for the thermal field double. So I haven't thought carefully about whether they're true more generally. So yeah, I should probably add a sort of caveat here.
And if you want the inequality to point in the same direction as the volume one, so that the two proposals are consistent with each other, like what does it imply about the choice of LC?
So like if you choose, all that ends up mattering, for at least for our calculation, is the ratio of LC to the ADS radius.
Oh, okay.
So if you choose, for example, that it's just equal to the ADS radius, then it has the same direction as the volume.
Okay.
You need to make it, let's see, I forget. You need to make it smaller than the ADS radius by a certain factor, and then it will change. It'll be still subadditive, but if it's bigger than that, it'll be superadditive.
Okay, so basically you're saying that like if you take LC to be of the order of the UV regulator on the boundary, then it's gonna be as without this term.
Yeah, then if you take like LC just be the ADS radius, say,
okay,
then it'll be actually superadditive, like the volume.
Okay, thanks.
Yeah. Okay, so let me just specify the calculation a little bit more precisely. So we're just considering now CFTs. So hyperscaling is all we haven't thought about that complication. So just CFTs, Pfefferman-Graham coordinates. This little z is now the radial coordinate, not the dynamical exponent, and you have the usual black hole factor here. And the entropy, importantly, is the volume of the CFT in ADS units, and then you have this factor of 1 over the horizon position, which is like 1 over the temperature. So z is here a length scale. And as the black hole gets cooler, the length scale gets longer. Okay, so you can do the calculation for the volume or action of these patches. Volume something, there's a UV divergent part, and then a part with a positive sign here, which is 1 over the horizon position to some power. So this is basically think of this as plus the entropy. And then if you do the action without the counterterm, you get another UV divergent part, and then a part here, which is also plus the entropy. But there's an additional factor of the horizon position divided by the cutoff. So here we've actually made a particular choice for the normalization of the joint terms in the perimeter calculation. In fact, if you made a different choice there, you would get a slightly different answer here. But the key thing is this roughly goes like entropy, which is this factor times log of entropy. So it has a kind of interesting, it's not quite what we expected. We expected something which is of order entropy. Here we get something of order entropy log entropy. But it is positive for a low enough temperature. Now, if you add the counterterm, you get a different thing. Now you get a UV divergent piece here. Sorry, for some reason I changed the notation from delta to epsilon, but this is the UV divergent piece. You see that LC appearing. And then over here you have some part which is just proportional to the entropy. That's the 1 over ZH to the D minus 2. But there's a factor which depends on this constant. This is a constant G naught, which is negative, just some fixed number. And then a factor here which depends on the ratio of the cutoff, the counterterm parameter LC, and the ADS radius curly L, and a factor of the dimension. So basically, you as you adjust the ratio here, you can make this term negative or positive. And that's the origin of the ambiguity in whether it's subadditive or superadditive. As mentioned, this was also pointed out in the paper by these authors, that if you include the counterterm, then you can get a different answer, and this will appear in the updated version of our paper, which should be on the archive soon. Okay, so with the counterterm, it seems like you really can kind of get whatever you want, and it's not clear what the choice should be. If you choose they advocated choosing the thing so that the UV divergent term is 0. If you do that, you zero this term out, then I think the answer is that it's super additive, like the complexity equals volume prescription. Okay. I'll just mention you can check other things. You can check, for example, Shockwave geometries. In the thermal field double state, the complexity of the left or the right are time independent because they're just exact thermal states, so nothing happens to them, and that follows immediately from this prescription. But if you perturb, say, the left with a shockwave, with a precursor operator at early time down here, then although at late times the geometry looks like that of a quiescent black hole, it looks like it's in thermal equilibrium, actually the quantum state is changing as a function of time. And one can do the calculation and find that the rate of growth of the action of just the left is 2m. The rate of growth of the right is 0, as you would expect, because it's still in an exact thermal state. And so you actually recover your expectation that you get the 2m from this subsystem complexity story. And you see that it comes all from the left. Okay, so now I'd like to finish up by talking about what the left-hand side of C equals A or C equals V means, especially in the case of mixed state complexity. So the first thing I like to point out is that in principle, there's a difference between what you could think of as mixed state complexity and subsystem complexity. Mixed state complexity should be something which assigns a complexity to any mixed state whatsoever. Subsystem complexity is something which would assign a complexity to a subset of degrees of freedom in a total pure state. So in the case of the subsystem complexity, you could imagine that using some structure of the bigger system as part of the data that you use to define your complexity. So in other words, subsystem, we really view it as part of something bigger. For mixed, we really think of it as just something that should exist on its own, independent of whatever the detailed rest of the universe is doing. And here we're going to kind of take the point of view that we're interested in some mixed state notion. So we won't really use anything about the fact that the system is entangled with some larger world. We'll forget about everything else and just focus on the density matrix of the subsystem. And then there's various approaches to define the complexity that you can think about. So to set things up, we imagine we've fixed some definite notion of pure state complexity. So that's fixed from the start. We've made our choices. We have a notion which can be applied to any set of qubits, say. And so probably the most obvious thing to say is that the complexity of a mixed state could be taken to be the complexity of the minimum purification. So in other words, we look at this mixed state, we look at all possible purifications of it, which is a pure state. We compute the complexity of each of those purifications. We minimize that over all purifications. And that's what I denote curly C sub P, the purification complexity. I think that's a fairly natural thing. It's just saying you need to prepare the mixed state somehow, but you don't have to do anything special on the purifying system. You can make that as simple as possible. And that's what you would mean by the complexity. Now, another approach, which is sort of more of a spectrum basis approach, is to think of the complexity as having sort of two pieces. The first is that this mixed state has some non-trivial spectrum of eigenvalues. And so we could ask, say, for the complexity of purification, where we don't require to recover the same density matrix with just the same spectrum. So in other words, we don't have to have the basis correct, but we just have to have the spectrum correct. That we denote curly C sub S, the spectrum complexity. And clearly, because the actual state has the same spectrum as the same spectrum, it means that CP is bigger than or equal to CS. So basically, it takes more work to get the basis right in addition to the spectrum, as opposed to just getting the spectrum right. And then we have a natural notion of basis complexity, which is sort of the complexity of getting the right basis given that you have the spectrum sort of for free in some sense. There's two different ways of defining this, which I call CB and CB tilde. So CB is very naive. It just says, let's take the purification complexity and subtract from the spectrum complexity. So that's roughly speaking how much extra work we need to do to get the basis right. And as I said, that's guaranteed to be positive or to be non-negative. Now we might also say, let's start from the minimum complexity state with the same spectrum, and then ask how many more unitaries we need to apply to get to the physical state. That I call CV tilde. And you might guess this is roughly the same as CB, but it's not clear at this level of generality what the relationship between these two things is. And there are other possible approaches as well. We could also take a sort of open system approach where we, instead of applying unitary maps on a bigger system to make a pure state, we apply quantum channels. We apply open system dynamics to our system. And then you could, have even other possibilities. For example, every mixed state can be viewed as an ensemble of pure states in many different ways. So in what we call the ensemble approach, you could imagine, say, looking over all possible ensembles, which give you the given mixed state, computing the average complexity of that ensemble, and then minimizing overall ensembles. That would be another notion. And at this level of generality, it's not clear how any of these things interact with each other beyond some relatively simple inequalities you can prove. Okay. So what I'd like to do now is to take these different possibilities and sort of try to compare them to the holographic result and also the tensor network expectations and see what we can get out of that comparison. Yeah, before I go, there's a picture which kind of explains. So here's a reference state. Here's the blue blob is a space of states with the same spectrum as rho. So CS is like just the minimum distance to get inside that blue blob. That's rho spec. CP is minimum distance to get from the point, the reference state, to the target state. And CB tilde is how far you need to go from this minimum spectrum state to the target state. So there's a kind of nice picture there. Now, to get a sense of what the physics should look like, let's ask about the tensor network expectation. If I have, say, n qubits and a Mara-like network for the ground state at t equals 0, then you would expect that the purification complexity is just the actual ordinary pure state complexity, because it's already a pure state. And I get some constant k1 times the number of qubits. That just follows from counting the number of gates in Mara. The spectrum complexity is 0 because there's no spectrum. It's just trivial. And the basis complexity is exactly the same as the purification complexity. If you take a Mara-like network with a thermal cutoff, then you would expect something like this. The spectrum complexity is now proportional to the entropy, because roughly I need to make entropy number of bell pairs, and each bell pair takes an order 1 number of gates to prepare. So I would expect something of order the entropy times a constant alpha that I don't quite know about. Similarly, for the basis complexity, I would expect that you have essentially the original complexity of the full ground state, and then I subtract from it something which is also proportional to the entropy, which corresponds to taking that Mara network and deleting all of the tensors that are at scales longer than the thermal scale. So in other words, I lose all correlations beyond the thermal scale, and I only have the sort of UV correlations, and that's the UV part minus the thermal scale part that I've lost. And then you can also think about infinite temperature, which is kind of the opposite extreme limit. There, the purification and spectrum complexity are the same because the state is just the maximum mixed state. So the only state with the same spectrum as that is itself. So it's proportional to the number of qubits, and then the basis complexity is both 0 because there's no basis to change to. All the bases are the same. So let's do the matching. So first of all, without the counterterm, as I said, what you get is that the twice the complexity in the action way of thinking of the left or the right is bigger than the complexity of the thermal field double. Whereas for CV, you get that twice the complexity is exactly equal to the thermal field double complexity. And we found from our calculation for without the counterterm that the action was like the number of qubits, where that's basically the volume in cutoff units plus s log s, and that the volume is the number of qubits plus s. Okay, so without the counterterm, or with the counterterm but keeping subadditivity of CA, then first of all you see that CA increases with temperature, right? It's proportional to s log s, so as the temperature goes up, CA goes up.
So Brian, I'm a bit confused.
Yeah.
And the confusion comes from the fact that, like, for the term of a double slit, you can pick like arbitrary time slices on the left and the right.
Oh yeah. Here I'm doing time 0.
Yeah, but like the reduction to the subsystem complexity on each side would be the same, right? Because the system is translation invariant, I guess.
Yeah, that's right. So this inequalities or these statements are only true at 0 time. Okay. Eventually, the right-hand side is always bigger than the left-hand side because these are exactly invariant, independent of time.
Because at very late times, you imagine that the total complexity of the state is way bigger than the complexity. That's right.
That's right. So I'm doing every comparison I'm making is at time 0 at the time symmetric slice.
Okay.
Yeah, that's right. And I guess the interesting thing is that even at that slice, you can actually get some mileage out of this because you have all these different inequalities that you can play with.
Okay, thanks.
Yeah. Yeah. So back to what I was saying, the CA increases with temperature. That's not expected to happen for basis complexity. Remember, we said the basis complexity should decrease with temperature, roughly speaking. So it can't be basis. It's UV sensitive. That shouldn't happen for the spectrum complexity, so it doesn't seem like it's spectrum either. And it's subadditive, which we actually expect for the purification complexity, roughly speaking. The reason is that when you prepare the density matrix of one side, you have to prepare the basis of that one side plus the spectrum, which is basically those order S Bell pairs that connect left and right. So if you do that twice, you prepare the basis twice, which is the same as the basis on the left and the right, and you prepare the spectrum twice. However, when you do the thermal field double, you have to prepare the basis on the left and the right. That's the same. But you need to prepare the spectrum only once, because you can use the same spectrum for the left and the right. That is, one side of the spectrum is the same as the other side. And so it's natural, if you have this sort of basis plus spectrum complexity, if the complexity of the thermal field double or the mixed state is roughly a basis part plus a spectrum part, it's natural that CA would be subadditive if it was a purification complexity, because then you only have the spectrum once for the thermal field double, but twice for the 2 copies of the subsystem. And I'll just comment that CV has the property that thermal field double is exactly equal to twice the subsystem complexity. And that's not expected for any measure absent some fine-tuning. So we were not able to think of any measure of complexity which would naturally reproduce this fact. So I think that's an interesting open question. One possibility is you could modify complexity equals volume when you have an RT surface to say maybe you can add some term which is proportional to the entropy, for example. Like essentially a term localized on the RT surface. That would be, you could do that. I don't know why you would do it, but you could do that. And then you could probably make CV compatible with some of these measures. But as it stands, it's not obvious how to think about it. Now, with the counterterm, and assuming that you have changed from subadditivity to superadditivity, then you have the property that CA actually decreases with temperature. And that's what's actually expected for basis complexity. It's still UV sensitive, so it can't be a spectrum. And it's superadditive, which is not expected for the purification. So now it looks more like basis if you have the superadditivity. The reason, again, being that now twice the subsystem complexity is just twice the basis complexity, which is the same as the complexity of preparing the basis on the left plus the basis on the right. Whereas the thermal field double is twice the basis complexity plus the spectrum complexity. So you have to prepare the spectrum now, which you didn't have to do for just the basis on the left and the right. So it's kind of natural then that the thermal field double would be bigger than twice the subsystem complexity. So the conclusion seems to be that essentially amongst these measures we defined, you can get one that matches CA no matter how you choose the counterterm, whether it's subadditive or superadditive. None of them seem to match CV very precisely, but it's still sort of a confusing situation. So, my original guess actually was that subsystem CA would actually correspond to the basis complexity. When Matt and Cesar and I started that work, that was my guess. It was sort of the outside part. So it's like the RG part of the tensor network. And the interior of the black hole is like the part that prepares the entanglement between the two sides. But then we found that it didn't seem to match that expectation. So we sort of cooked up this complexity purification story to match that. Now, maybe if you choose the counterterm in a certain way, then finally suddenly this basis complexity looks reasonable again. Although it's still a little weird because the outside clearly knows about the spectrum. But maybe for some reason that's what CA is computing. So basically the story is CV doesn't seem to match any interpretation very well, although there's not a really sharp contradiction, but it just doesn't seem to match what we would expect. Depending on whether the CA is subadditive or superadditive, you can actually get either something which looks like the complexity of purification or the basis complexity. And so it really raises the question, what's going on with this counterterm? What's the interpretation of it? How do we think about it? How do we fix it? And rather, there is this ambiguity there. I said there's a lot of ambiguity in complexity, but this seems like a little bit more ambiguity than one would like. It seems like you should definitely, CA should either be basis or purification or something else, but not sort of all of them at once, depending on this choice. Well, maybe that's too naive. I don't know. Maybe, the surfaces of the null surfaces are sort of associated to some extent with the entanglement between the system and its complement. So maybe actually it is like changing, in essence, whether you're counting the entanglement or not as part of the complexity. So, I don't know. But that's all I have to say. So thanks for paying attention, and I can take any additional questions now.
Any more questions? Or from people online? Since I haven't muted them all. Okay. All right, I guess if there's no other questions, then let's thank Brian again.
All right, thanks.